Good morning. So this is a video session for the program BSc, subject Mathematics, semester 5, session 28, and this is about the comparison tests and also some theorems. So comparison tests. So this is the learning objective. This is the session outcome. These are the prerequisites. So here we need what is bounded function, what are convergent and divergent functions, then infinite discontinuity. So comparison tests. So here one theorem is there. So that is a necessary and sufficient condition for the convergence of the improper integral a to b f of x dx at a, where f is positive on the open interval ab, is that there exists a positive number m independent of epsilon greater than 0, such that integration from a plus epsilon to b f of x dx is less than m for all epsilon in 0 to b minus a. So we prove this theorem, as we know that since a is the only point of infinite discontinuity of f on the closed interval ab. So therefore f is continuous on this semi-open interval ab. So semi-open interval ab means the end point a is not included, because a is the only point of infinite discontinuity. So therefore it is continuous at all points other than this point a. And also f is positive on this semi-open interval ab. This means for a less than a plus epsilon less than b, f is positive and continuous on a plus epsilon comma b. So which implies integration from a plus epsilon to b f of x dx represents the area bounded by f on the interval a plus epsilon to b and the x-axis, because this is the integration means what? By the definition of the integration is nothing but it is the area bounded by the function f and the x-axis. So therefore this represents the area bounded by f and the x-axis over the interval a plus epsilon to b. This means as epsilon tends to 0 plus, this a of epsilon increases because as epsilon tending to 0 means the points are increasing. So therefore length of the interval also increases, which means limit as epsilon tends to 0 plus a of epsilon is equal to limit at epsilon tends to 0 plus integral from a plus epsilon to b f of x dx will exist finitely if and only if a of epsilon is bounded above. If this exists finite, if a of epsilon is bounded above means what? If it exists finite, then clearly there exists a number m such that this a of epsilon is less than or equal to that number m. Okay, so this means integration from a to b f of x dx will converge if and only if there exists a real number m greater than 0 and independent of epsilon such that a of epsilon is less than m, which means integration from a to b f of x dx converges if and only if integration from a plus epsilon to b f of x dx is less than m for all epsilon in 0 comma b minus a. So this completes the proof of the comparison test theorem. So next we have a comparison test. So this is the statement: if f and g are two positive functions with f of x is less than or equal to g of x. So this f of x is what? Less than or equal to g of x for all x in the semi-open interval ab, and a is the only point of infinite discontinuity on the closed interval ab. Then the first one, integration from a to b g of x dx is convergent, implies, means if this is convergent, then integration from a to b f of x dx is also convergent. Second one, if a to b f of x dx is divergent, this implies integration from a to b g of x dx is also divergent, right? So now we prove this theorem. Now since f and g are positive and f of x is less than or equal to g of x for all x in the semi-open interval ab, which means that integration now by integrating this equation, which means integration from a plus epsilon to b f of x dx is also less than or equal to integration from a plus epsilon to b g of x dx for 0 less than epsilon less than b minus a. So this means now we assume that let integration from a to b g of x dx is convergent, right? So by the definition of the convergent, then there exists a positive number m such that integration from a to a plus epsilon to b g of x dx is less than m by the definition of the convergent for 0 less than epsilon less than b minus a. So therefore integration from a plus epsilon to b f of x dx is less than epsilon, because this is less than or equal to this one. Okay, so and this is less than m means this is less than also less than m, or 0 less than epsilon less than b minus a. This means integration from a to b f of x dx is convergent. Now second, we assume that let integration from a to b f of x dx is divergent. Then by the definition of the divergent, then for every m greater than 0 there exists epsilon in 0 comma b minus a such that integration from a plus epsilon to b f of x dx is greater than m by the definition of the divergent, which means when this is greater than m, as this is greater than this one and this is greater than m, clearly this is greater than m. So that is integration from a plus epsilon to b g of x dx is greater than m. So which means integration of a to b g of x dx is divergent. Okay, so this completes the proof of the theorem, and with this I conclude this session. Thank you.